Hello, everyone. Happy New Year, and hope everyone had a quiet, restful holiday. I'm your host, Brett Johnson, Program Chair for NACE Calgary, and back with a new season of webinars. Among the crazy, never-ending news cycle of the new year was an announcement from NACE headquarters of a brand new name. So with the successful integration of SSPC, or otherwise known as Society of Protective Coatings, our combined new technical society felt they should launch with a brand new name, and that great name is AMP, or also known as the Association for Materials Protection and Performance. So I don't know how that's going to impact our Calgary division up here, or when I'm going to need to, get a new poster back there or something. But I do know for now that everybody with a NACE membership is eligible for a dual membership with SSPC, and which you can enable with your NACE login at www.nace.org. So today's webinar features Chukwuma Onuoha from PureHM, a Xylem brand. Chuks is a global product manager for corrosion, covering cathodic protection and overline survey information. Chuks holds a Master of Science in Corrosion Control Engineering and a doctorate in Materials Engineering. He's also the author of over 30 corrosion technical papers and a researcher for PRTI. Chuks, we're super happy to have you join us here today. So do you want to give us a little introduction of what you're going to talk about today?
Thanks, Brett. Yes, today I'll be talking about the proven assessment strategies for defeating time-dependent threats. So the focus is going to be on external corrosion, internal corrosion, and surface corrosion cracking, in the oil and gas pipelines. So I'll be going through the methodologies, industry best practices, and then focusing on non-piggable pipeline segments. So that's just make it very brief.
Awesome, Chuks. Well, very much looking forward to it. So, before we jump into it, I'd like to highlight our annual sponsors. Their continued contributions allow us to be able to provide this webinar series to our membership at no charge. And today, I would like to highlight our gold sponsor, Stantec. Stantec believes that integrity begins with people. Their team of specialists have the technical and field experience to provide practical and creative solutions to ensure integrity of your assets. Their goal is to deliver safe, reliable, and integrity-compliant solutions to the oil and gas industry. Experts include inline inspection specialists and NACE-accredited corrosion, cathodic protection, and coating professionals. They aim to work collaboratively to provide comprehensive integrity strategies for their clients. And integrity just isn't a job for Stantec. It is who they are. And of course, to all our other annual sponsors are a huge reason why we can do what we do. Our sponsors help fund several initiatives that NACE Calgary takes on to promote the knowledge of corrosion, sustainability, and asset integrity to our industry and the next generation of engineers. To each one of our sponsors, we thank you for your continued support. So to see the recording from this webinar and all our other past webinars, be sure to check out our website at nacecalgary.ca, and from there you can be able to find the YouTube channel link. So Chuks has pre-recorded his presentation. Be sure to stick around after the presentation as we'll move into a live Q&A session. Please submit your question to Chuks in your Zoom client by clicking the Q&A button on the screen. And if you are joining us from YouTube Live, please enter your question into the comments and I'll be sure to ask them for you. So without further ado, let me here launch Chuks' presentation.
Hello, everyone. My name is Chukwuma Onuoha Chuks. I work with PureHM Xylem as a global product manager for corrosion, responsible for overline survey technologies and cathodic protection. Today, I'll be talking about proven assessment strategies for defeating time-dependent threats. Looking at internal corrosion, external corrosion, stress corrosion cracking in oil and gas buried pipelines. The focus of the seminar is going to be on non-piggable or difficult to pick pipelines. The presentation is based on proven methodologies, industry best practices, and I'll be wrapping it up with successful case studies. So have patience and enjoy the seminar. Part 2019 AER failure records. Internal corrosion contributed to 46%, external corrosion 12%, and similar FEMSA records from failure records from 1998 to 2017 show that internal corrosion accounted for 60% of all pipeline incidents caused by corrosion. Specifically, 12% of those are attributed to internal corrosion, 8% for external corrosion, and 1% caused by external stress corrosion cracking. So what does this tell us? It shows that buried oil and gas pipelines must be assessed to be able to prevent future failures. So how can we assess the integrity of these pipelines? There are generally three known pipeline integrity assessment techniques. The first one, which everybody is very familiar, is the hydrostatic pressure testing, which is very intrusive, destructive, and non-predictive. It's a pass and fail test. You cannot really use it to predict future corrosion mechanisms or corrosion failures. So you do the test now, it's pass and fail, and that is it. Inline inspection is generally accepted as one of the best ways of assessing integrity of pipelines. It is very intrusive, non-destructive, and reactive. So when I mean reactive, it has a detection threshold, and to a certain extent, the defect has to grow to a certain level before it can be identified. The last one is a direct assessment. So my focus for the whole presentation today is going to be focused on direct assessments on non-piggable pipelines. It is very non-intrusive, it's non-destructive, and it is predictive. Looking at external corrosion assessment, where technicians are working on the pipeline and they're capturing they're trying to gather information about the cathodic protection levels, the coating conditions, the depth of cover, the soil resistivity. Those information are used to be able to predict the likelihood of external corrosion. If the data suggests there's a problem, it can be proactively addressed to prevent future failures. So it's very, very predictive. For internal corrosion as well, robust and sophisticated internal corrosion predictive modelings are also available to be able to predict water, solid, and concurrent internal corrosion rates for the entire pipeline. And if you have such information, you'll be able to identify and prioritize areas of concern, mitigate them to prevent future failure. So it is very, very predictive. Each of these pipeline integrity assessment techniques have their pros and cons. But whenever possible, whenever practically possible, okay, looking at the economics as well, combining two pipeline integrity techniques is one of the proven effective ways of assessing pipeline integrity. For instance, when an inline inspection is run or used as a main pipeline integrity assessment technique, the ILI can report external corrosion metal loss, but the operator wants to know what caused that? Why did I have that problem? In that specific instance, you can actually use DA if ILI is the main integrity assessment technique for that, regulated, transmission pipeline in this specific instance. You can actually use DA, supplementary DA, as an engineering assessment to do root cause analysis. For instance, ILI reports external corrosion metal loss. You don't know what is causing that. You do a supplementary engineering assessment with the DA methodologies. You look at the cathodic protection levels, the coating conditions, and the soil resistivities. You integrate all this information. In addition, you can also, to be more holistic, you also assess the likelihood of AC, DC interference problem, MIC. You include all this information in a holistic assessment, correlating with that metal loss in the inline inspection to be able to pinpoint the root cause. Once you know what the root cause is, you can actually plan and refine your mitigation measures going forward. So all these techniques have their pros and cons, but whenever possible or whenever practically possible, combining the two is going to help you make an informed pipeline integrity decision. DA methodologies can be used to detect pipeline time-dependent threats. Like for the first one, everybody's very familiar with external corrosion direct assessment, stress corrosion cracking direct assessment, internal corrosion direct assessment, ICDA. These DA methodologies can be applied to both pickable and difficult to pick pipelines. It is a very systematic and it has very thorough and intensive thought process, which I'm going to cover in the next slide. The first stage of the DA is a pre-assessment. So stage one is a pre-assessment, which is a step one. That is when you gather all the information pertaining to that specific pipeline. You gather all the data, and then you're trying to screen the factors and confirm that this chosen specific inspection is the appropriate technique for that pipeline segment. So you collect the data, you confirm whether it is actually feasible to complete the inspection. If it is for external corrosion direct assessment or stress corrosion cracking direct assessment, you are trying to confirm, can I physically work on the pipeline? Are there conditions that can prohibit the completion of the indirect inspection and completing the digs, which is a direct examination stage? For instance, if you cannot work on the pipeline to be able to capture pipe to soil, coating survey data, and depth of cover, soil resistivity, if you cannot physically assess the pipeline to conduct the inspection, ECDA is not practical. So you have to assess, complete the feasibility, confirm it's going to be feasible, select your indirect inspection tools, and then select your regions. For the ICDA, that is when you are going to define the internal corrosion predictive modeling that you're going to use for the assessment. The step two is when, for the ECD and stress corrosion cracking direct assessment, this is when you have to work on the pipeline to be able to capture cathodic protection information, pipeline elevation information, the coating, soil, everything you can use to be able to predict for the ECDA likelihood of external corrosion. If it's for the internal corrosion assessment, that is when you are working on the pipeline. If you don't have the pipeline elevation profile, to be able to capture the accurate pipeline elevation profiles, and then use robust internal corrosion predictive modeling to be able to predict the likelihood of internal corrosion. So once you're done with stage two, you have figured out where the corrosion is likely possible, and then the stage three is when you have to expose the pipe, take some NDE measurements, do some remaining strength analysis and calculations, figure out what the root cause is. If I had external corrosion, why did it happen? If I have internal corrosion, what the problem is. Once you've completed that stage in stage three, the whole program is wrapped up in the post-assessment, and that is when you have to evaluate the effectiveness of the entire program, and then you can define the next time you're conducting that assessment, which is the reassessment interval. So it's a very thorough, intensive process. Step one, data. Stage two, work. Stage three, dig. And step four is when you evaluate. So this slide is showing the most probable locations, regarding where you have these, time-dependent threats from each specific DA. So you can see from external corrosion is outside of the pipe. Is outside of the pipe. You're looking at your CP, coating, and soil resistivity. Cracks external to the pipe. You're looking at the previous history, age of the pipe, coating, stress level, temperature, distance from compression station or pump, and you integrate this information to be able to assess the likelihood. For the internal corrosion, you can see from here that the low points on pipeline elevation profile can be used to assess the likelihood. However, that is not incomplete assessment, but it kind of gives you an idea. Where should I expect, for instance, for the dry gas, liquid petroleum, where should I have dropouts? For multi-phase and wet gas, you can see from this picture that you can actually have problem anywhere on the pipe, even top of the pipe, top of the line. So there are robust internal corrosion predictive modeling that are available to help you with these assessments. So if you go to next SP, if you go to the specific code, which I'm going to show in the next slide, there are reference modeling flow modeling that you can be used to be able to support you in this assessment. So this is the industry reference best practices and standards for all the DAs. The first one, the most popular, NEST SP0502, that's for external corrosion direct assessment. You look at your CP, coating, soil resistivity, you predict whether you're going to have a problem or not. For stress corrosion cracking, NEST SP0204 2015, that's for stress corrosion cracking direct assessment. So in this specific one, you look at your previous history of XCC on the pipeline, you look at the age of the pipeline, stress level, temperature for high pH SCC, distance from compression station for gas or liquid for high temperature, high pH SCC. You look at the coating type, then you integrate all this information to be able to figure out whether you are going to have a problem or not. So for the ICDA types, there's DG for dry gas, LP for liquid petroleum, WG for wet gas, and MP for multi-phase. All of them, they are robust and available internal corrosion predictive modeling that you can use to predict the likely general and localized corrosion attack, and they can even predict the internal corrosion rate for the entire pipeline. So for each specific type, go to the reference standard. There are recommended flow models that can be used for the specific inspection. For internal corrosion assessment on crude oil pipelines, the details are captured in NEST SP0208. So the evaluation relies on appropriate use of predicted flow modeling and using pipe elevation profiles to be able to predict water and solid accumulations and subsequent internal corrosion rates. So when you use these flow models, you predict water and solid accumulation locations, internal corrosion rates, and then you'll be able to prioritize areas of concern, mitigate them and prevent and make an informed decision to prevent future failures. So the basis is if I can assess where solids, water, or other electrolytes first accumulate, I can make an inference about the remaining downstream length of the pipe. So if I assess the worst case on the pipeline, I don't find any problem, I'll make a reasonable assumption that the other locations should be in good shape. So how do we assess? What are the assessment methodologies? First, you screen and complete the pre-assessment. You want to know, is LPICDA the appropriate integrity assessment method for this selected pipeline segment? All the information you need is detailed in Table 1 of SP0208. You want to know, can indirect inspection not able to determine where internal corrosion is possible? You want to know, does the pipeline have continuous water phase for the entire pipeline? Is the pipeline have continuous internal coating for the entire pipeline? Are there conditions that make it possible not to actually complete the detailed examination? Are there conditions that makes it not possible to define an accurate reassessment interval? So when you capture all the information and complete the reassessment, select all your regions, then you can confirm that the pre-assessment is feasible. Once that stage is completed, then the next stage is you want to predict the likelihood of internal corrosion. How do you do that? You can use multi-phase flow calculations, or you can use reliable internal corrosion predictive modeling with pipeline elevation profile to be able to predict water and solid accumulations and subsequent internal corrosion rates. And when you're doing this, with this information, you also look at previous history, current operating condition, so they can predict the future. So the way I look at it is, I want to assess the likelihood of internal corrosion first. I want to look at the past. If I know what happened in the past, I know what is going on now, that will give me the confidence and a lot of information to predict what is going to happen in the future. But I need all this information to be able to make that call. This picture shows, I was talking about a robust internal corrosion predictive modeling. If you need more information on this, you can go to the appendix section of NACE SP0208. There are a lot of recommended flow modeling that you can employ to assess your pipeline segments for non-pickable pipelines. So this shows you how the flow modeling can actually give you the corrosion rate for the entire pipeline, and for the corrosion rate for the entire internal corrosion rate for the entire pipeline, water and solid accumulation locations, and if you want to select your digs, you can actually use this information to refine where you're going to expose on the pipeline. So once you have ranked or prioritized your dig locations, you expose the pipeline, assess the condition, compare what was predicted and the actual, complete all those assessments, then you wrap up the entire assessment in the post-assessment stage. So that is when you are trying to assess the effectiveness of the program, and then you're trying to define the reassessment interval. And that is, what am I going to do the next inspection? The next one is the dry gas, which is the DGIC, the Dry Gas Internal Corrosion Direct Assessment. So all the methodologies are specified in NACE SP0206. So the evaluation of the likelihood, relies on, as I said earlier, you can use, multi-phase flow calculations, or you can use predictive flow models and pipeline inclination profiles to be able to predict water accumulation locations and internal corrosion rates for the entire pipeline. So the background is that if I can assess the worst case where I should expect water on the pipeline, I don't find any problem, it helps you make an informed decision about the remaining segment of the pipe. Normally, during detailed examination, you select, that the upstream where the first locations where you expect water dropout, and then you try and actually do another validation at the downstream to ensure that there's no internal corrosion for a representative location to show that there's no internal corrosion for the entire pipeline. So what are the methodologies? Similar concept. First of all, you screen, you complete a pre-assessment. You want to determine, is DGICDA the appropriate integrity assessment method for the selected pipeline segment? So that will require detailed information about the potential internal corrosion that the pipeline has been in history. All the information you need is documented in NACE SP0206-1. So you want to know if does that pipeline have history of top of line corrosion? Are there a lot of interconnect and outlets that makes region solution complicated? Has the line historically been used to transport crude oil or other liquids? Is the pipeline internally coated? You look at, has the pipeline been peaked? Is there any confirmed accumulation of solid, sludge, biofilms, biomass? Is the pipeline diameter less than 4 inches and greater than 48 inches? Is the operating pressure greater than 11,000 psi? If the pressure is greater than 11,000 psi or the diameter is greater than what is shown on this table, that means it might not be the best appropriate assessment technique to be used. So you screen, you complete that pre-assessment, you confirm that DGICDA is feasible, and then you can go to the next phase. So the next phase is you want to predict the likelihood of internal corrosion. You can perform multi-phase flow calculations to determine the critical inclination angle of liquid holdup, or you can use appropriate ICPM, which is internal corrosion predictive models, and pipeline inclination profiles to predict water accumulation locations and concurrent internal corrosion rates for the entire pipeline. In addition, you can also use dew point curves. They are phase envelopes, pressure temperature curves to be able to confirm likelihood of water condensation. So you need an electrolyte to be able to initiate an internal corrosion. So phase envelopes, dew point curves, all those will be able to predict likelihood of water condensation based on current operating conditions. When you're doing this assessment, again, consider the past, the current, operational condition, and use that information to be able to predict what the future likelihood is. So for your flow modeling, you're going to need accurate pipe elevation profile. You can get that from as built, or you can use integrated ECDA indirect inspection techniques that captures the GPS mapping and depth of cover in one inspection to be able to capture your accurate pipe elevation profile for your ICDAs. So once you have completed that, maybe you're using the flow modeling, you have predicted where you have water and water accumulation. You select those locations for detailed examination. You have exposed the pipe. You confirm what was predicted and the actual, and then you can do your NDE measurements. And then the whole program is wrapped up during the post-assessment stage. You want to assess how good the effectiveness of the program, and then you can select your reassessment interval. So for instance, in the US, for gas pipeline, for dry gas pipeline, if you don't have any internal corrosion found, the reassessment interval is automatically 7 years. So for each specific type, you want to know what the reassessment interval, which is driven by the condition of the pipe. The next one I'm going to talk about is stress corrosion cracking on buried onshore pipelines. So detailed methodologies are captured in NACE SP0204. So the evaluation of stress corrosion cracking likelihood on onshore coated and cathodically protected pipelines relies on, you want to look at, have I had previous XCC on the pipeline? What is the operating stress level? The distance from compression station or pump station, for high pH SCC, what operating temperature is for high pH SCC, the age of the pipeline, and the coating type. So generally speaking, for XCC to happen, the susceptible material or pipeline material in this instance must be exposed to environments conducive to stress corrosion cracking. For NACE SP0204, there are two types of SCC that can be assessed. The first one is a low pH and high pH. So the likelihood assessment factors like the previous history, age of the pipeline, coating type, stress level, those ones can be assessed for the both types. But temperature, distance from compression station or pump station for liquid, those ones become, those factors are now more unique to high pH XCC. So when you're doing the assessment, temperature and distance from compression station or liquid, they are now used in addition to the previous history, age, coating type, stress level, to be able to assess for the high pH. So what are the methodologies? Similar concept. You screen, you complete your pre-assessment. You want to determine, is XCCDA the appropriate integrity assessment technique needed for this pipeline segment? So that will require detailed evaluation of the likelihood. All the information you need is documented in NACE SP0204 2015 latest version. So for instance, you want to know, has there been any previous SCC? No problem. Operating stress level greater than 60, age of the pipeline, coating type is FBE, or it's not FBE. You look at the operating temperature if you're assessing the high pH SCC. Distance from compression station for gas or liquid for pump station for liquid for high pH. So you want to integrate all those information to be able to assess the likelihood. So once the pre-assessment is completed, then depending, the indirect inspection for XCCDA is not mandatory, but to be more holistic, it's actually recommended to be able to complete that. So you can actually work on the pipeline similar to external corrosion direct assessment program, capture your CP SIPs to identify areas of inadequate CP per NACE SP0169. You assess the coating condition from above ground. There are 3 techniques you can use. Alternating current voltage gradient ACVG, direct current voltage gradient DCVG, then alternating current attenuation, which is the ACCA to identify coating anomalies. There's also a new technology called large standoff magnetometry. It is used from above ground to be able to identify stress concentration areas. So I have my location that don't have good CP. I have coating fault locations. I have locations with stress concentrations. Then I can correlate that with soil resistivity, pH, and terrain information to be able to further refine susceptible areas. So once I'm done, then I have to refine those coating anomaly areas, location with inadequate CP, stress concentration zones, and if the pipeline is actually piggable, and I have information on reported external meta, I can correlate those information, the coating fault locations, coating anomaly locations, locations with inadequate CP, stress concentration, the pH, and soil information. I can correlate that to reported external meta loss dents or areas of coating disbondment, especially on pipeline coated with high dielectric coatings that shields under disbondment. So once I'm done with that, then you have to classify all those indications and then prioritize them based on your risk ranking. So you develop a risk matrix to be able to select direct examination based on the priority. So the entire program is wrapped up in the post-assessment to assess the effectiveness and define a reassessment interval. So the external corrosion direct assessment, which is the most popular, details are captured in NACE SP 0502. So the evaluation of external corrosion on buried, coated, and cathodically protected pipelines relies on evaluating the level of cathodic protection, coating, and soil corrosivity. So the basis in ideal condition, when I mean ideal condition, if a pipeline is cathodically protected, there should be low likelihood of external corrosion per NACE SP 0169 2013 standard. So locations where you don't have good CP with a lot of coating anomalies plus high conductive soil, that is where you should expect high likelihood of external corrosion. Methodologies. First, you screen and you complete a pre-assessment to determine is ECDA the appropriate integrity assessment method for this selected pipeline segment. All the information you need is detailed in NACE SP 0502 Table 1. You want to know, are there conditions that can actually prohibit completing the program? For instance, are there any conditions that makes it not practically possible to assess the pipeline, to do CP, or conduct the detailed examination, or there's a lot of rocks, or the pipeline is frozen in a thick ice, or there's interference currents that cannot be mitigated? All the problems that can prohibit completing the indirect inspection or the detailed examination, if those conditions cannot be addressed, you might want to rethink about whether ECDA is a adequate assessment technique for that specific pipeline. So once the pre-assessment is done, is feasible, you have selected your indirect inspection tools, one that will tell you about the levels of cathodic protection, and the other one that will tell you about the coating conditions. You have selected all your regions, and then you go to stage 2. Then you want to predict specific location that has a likelihood of external corrosion. So to do that, you do your CP-SIPs, which is cathodic protection closed interval potential survey, to identify areas of inadequate CP per NACE SP 0169. You conduct your coating surveys. There's 3 types: ACVG, DCVG, and ACCA, to identify your coating anomalies. In addition, you do your soil resistivity to assess the soil corrosivity. You integrate all this information to be able to predict likelihood of external corrosion. So the figure I'm showing on this slide is the advanced ECDA indirect inspection technology. You can see from this picture that this technology enhances the success of ECDA programs, because all soil resistivity, GPS, depth of cover, depth of water, TP, DCVG, ACVG, ACCA, all this information is collected in one pass. And if you collect all this information in one pass, it's going to enhance the success of aligning the indication and enhance the confidence in selecting location for direct examination, and also improve the overall process. So there's a lot of improvements in the industry, on the technologies that can be used to complete a successful ECDA programs. So once you complete all the inspections, then you have to align those indications. So looking at this figure, you can see the CP-SIPs. The green line is the on, the red line is the off. Down, you see the ACCA, which is alternating current attenuation. The blue line is the current level. So you can see a drop in the current level, which is as a result of poor coating quality. The red zone means high attenuation rate. So drop in current, high attenuation rate, that means there's a high current leakage from that coating fault location. And there's a peak and also indication on DCVG. So you have current drop on ACCA, spike on the ACVG, and with DCVG, that suggests there's a likelihood of coating indication in that area. So you align. So these advanced ECDA technologies make it easy for you to align these indications. So once you align those indications, which as you're seeing on this slide, so the left-hand side is the prediction. So this is, you look at the data, you predict this is the location that you should have a coating fault. On the right-hand side is the exact location that when the pipeline is exposed. So as you can see from here, there's a confirmed exposed pipe showing coating fault. So you predicted that there's going to be a coating fault at that specific coating anomaly at that location. The pipe is exposed and the coating fault is confirmed. So that tells you the confidence and the strength of advanced ECDA indirect inspection techniques. You can actually confidently predict the likelihood or the condition of the pipe even before you dig up the pipe. So you align those indications, then you refine, severe, moderate, and low, and then you prioritize them into immediate, scheduled, and monitored, and then complete your direct examination. So once you have exposed the pipe, do your NDE measurements, remaining stress calculations if required, do your root cause analysis. So you have completed all the requirements in stage 3. Then the program is wrapped up in the post-assessment, where you have to assess the effectiveness of the program, and then you can define the reassessment interval. So now I'm going to go into case studies. So, the first 27 slides, I was focusing on the background and methodologies. So this is now proving successful case studies based on using these methodologies. The first one was completed on a 30-inch crude oil pipeline. It has been in service since 1987. There has never been any failure or internal corrosion reported on this pipeline. But the operator wanted to know, do I have any problem? So all the screenings were completed per NACE SP0208 and found out that LPICDA was the appropriate assessment technique for this pipeline. So the robust internal corrosion predictive modeling was employed, and the modeling predicted that internal corrosion, there was high likelihood of, very low likelihood of internal corrosion in the pipeline. The pipeline was exposed to be able to confirm what was predicted in the modeling. And as can be seen here, you can see the note from the NDE report. There was no corrosion found after the NDE using AUT, automated ultrasonic techniques. So you can see all the methodologies in NACE SP0208 were employed. Internal corrosion predictive modeling was used to be able to predict water and solid accumulation and concurrent internal corrosion rates for the entire pipeline. To go one more step, we don't stop there. Then you want to confirm by digging up the pipe, do I actually have a problem? So during the detailed examination, the pipeline was exposed and NDE was conducted and there was no internal corrosion found. So the prediction in stage 2 confirmed confirmed in stage 3 when the pipe was actually exposed. So what this tells you is that if the methodologies are done properly, you follow the industry best practice, you're going to have a high likelihood of success. The next one is internal corrosion assessment on a dry gas pipeline. So the specific reference is NACE SP0206. So the screenings were done, the diameter is 20 inch, so it is within 4 to 48 inches allowed for the program. You can see the pressure, it is 1070 psi. It is lower than 1100 psi allowed for the program. So in this specific instance, all the screenings were done, per NACE SP0206, and the regions were selected, and DGICD was found acceptable technique for this pipeline segment. In addition, dew point analysis were conducted to show that water condensation was not practically possible based on the current operating conditions. So based on this, it was, it was concluded that the likelihood of internal corrosion was low. To confirm that, the pipeline was exposed, NDE techniques were done, and you can see from here, no internal corrosion was found, as predicted by internal corrosion predictive modeling, and as also confirmed by dew point analysis, and also confirmed by methodologies per NACE SP0206. Case study 3 is on stress corrosion cracking. So this specific case study is another example where combining two indirect inspection techniques, two pipeline integrity assessment techniques can improve the success. So in this instance, inline inspection was run, MAT2 was run, and it showed areas of coating disbondment. And then XCCDA program was completed. You look at the pre-assessment information like stress level, temperature, distance from compression station, age, coating type. The pre-assessment was done, and there has been previous history. So the likelihood is high. To go one more step and to be more holistic, the indirect inspection was done as well, and it showed high likelihood. There's a lot of coating anomalies predicted. And then, based on the overall assessment, it was determined that the likelihood of XCC was very high. That's the specific locations. The pipe was not protected by NACE standards. You see the pipeline elevation profile, there were DCV and ACV indications, and there were stress concentrations in that zone. The pipe was exposed as predicted in stage 2. Likelihood of ACC was predicted high. The pipe was exposed and near neutral ACC was found as predicted. So what did that entail you? If the methodologies are done correct, following industry best practices, you're going to have a high likelihood of success. The final case study was on external corrosion assessment on buried onshore gas pipeline. Following the methodologies, the pre-assessment was completed, regions were selected, indirect inspection tools were selected, and it was deemed appropriate for this specific pipeline. In stage 2, the technicians work on the pipeline, capture the CP, coating indications. In addition, soil susceptibility to corrosion was collected, was evaluated. And then the good thing about this specific case study was also demonstrates the benefit of combining two pipeline integrity assessment techniques. So in this specific instance, inline inspection was initially run, and the inline inspection reported clusters of external corrosion metal off in a specific span. So the subsequent ECD in this specific instance was actually driven by the problems reported by the ILI. So you can look at the value of combining the two inspection techniques. So the ILI reported metal loss, and the client wanted to know why. So the client wanted to go and do a supplementary ECDA to figure out what's going on. So looking at the data, it shows the pipe was not protected, high susceptibility to corrosion, there is stress concentration in the area, and based on this information, it was determined there's a very high likelihood of external corrosion. So that's the data. You can see there's a big dip in the CP. There's indication from attenuation survey, ACCA, in addition to ACVG and DCVG. So looking at this span, there's a likelihood that there's going to be external corrosion. So this is when the pipe was exposed and NDE was completed and external corrosion was found as predicted. So you can see the range of metal off that was found. So what does this case study tell you? So from this case study, the following can be deducted. One, when you use two integrity assessment techniques, you're going to have high level of success. Inline inspection was run and showed, external metal loss. DA was completed to be able to identify why. So in this specific instance, it was because the CP was not meeting the NACE criteria, and there were a lot of coating indications in the area. There was high susceptibility to corrosion. And then with this information, the pipeline was exposed and confirmed what was predicted. To be able to mitigate this problem, the client went on, recoated the entire segment, and the CP was improved. By doing that, that is going to prevent future external corrosion and external stress corrosion cracking problems. So this also shows that if you combine inline inspection and DA, or you can use inline inspection as a main assessment technique if it is a piggable pipeline, and then use DA as a supplementary engineering assessment, whichever, you're going to have high likelihood of success. It's also going to help you to be able to prevent future failures. So thank you for having the patience for 40 minutes to wait for me to go through the slides. And if you have any specific question or follow-up clarity, you can feel free to send me an email. I have 15 minutes for questions. I might not be able to capture all the questions during the short time frame, but you can send me an email, and then we can have an offline discussion, and I can address every question you have. I've done a lot of case studies on this stuff, and I can provide you the information that you need. Thank you.
All right. Well, thanks, Chuks, very much for that presentation. That was really good. So as Chuks mentioned in his presentation, we're a little bit short on time. We have a little bit of time left here. We have pretty hard stop just here before 1. So I'm going to jump just right into the questions here. So first, Chuks, when you mentioned that ILI is considered a reactive technique instead of proactive, do you want to just expand on what you mean by that?
Okay, yes, I got that question on the Q&A. So basically what I meant was, for instance, if you're doing a DA program, you have a buried, coated, and cathodically protected pipeline, you can, look ascertain the level of cathodic protection, confirm the condition of the coating, look at the soil conductivity. You can use that to predict the likelihood. So on the ILI, for instance, it is the best pipeline integrity acceptable technique. However, every tool has a drawback. So for instance, ILI has a detection threshold. So that defect you're trying to detect, it has to happen in the pipeline to a certain level before you can actually detect it. So that makes it very reactive. While in the DA world, I can look at my cathodic protection level, I can look at the soil resistivity or conductivity, I can look at the coating conditions, I can predict the likelihood. I can predict that in a DA condition, I don't have MIC issue, I don't have AC issue, I don't have DC issue. Based on this condition, I should not have any problem. But in the ILI world, it's the best tool. However, there has to be a threshold before the ILI can detect that threat. That's basically what I mean by reactive.
Yeah, ILI will show you that you've already had a problem and it may be already too late by that point.
And for instance, you can even have a problem, it cannot detect it because it does not reach the detection threshold. You know what I mean?
Yeah, exactly. Because if it's something small at that point, you may have a false indication that your pipe is fine, but something's already started at that point. And by the next time you inspect it, it could be way more deeper and susceptible than you think. Right?
Absolutely. And also, just to add to that, that also reinforces the value. I think somebody asked that question of incorporating different techniques whenever economically possible and whenever possible in overall. So for instance, you can do your internal corrosion assessment programs. You can use your robust internal corrosion predictive modeling. To an extent, you can even predict internal corrosion rates that are lower than the detection threshold of ILI. You know what I'm trying to say? So that's basically what I'm trying to explain.
No, awesome. Thanks for that. So, Chuks, I noticed in each of your case studies, the findings match the models that you end up using, but that doesn't always happen so conveniently in real life. So how should one adjust their DA program when their validations aren't lining up with their predictions?
To answer that question, it goes back to what the intent is. If the methodologies are done appropriately, if you're following the industry best practice, for instance, you're doing your overlying survey, inspections, And then you have a very good field procedures. Like if you're doing coating survey, you go to NACE TM 109. And for CP, you go to SP0, there's a TM 497, 227. Look at all those codes. Make sure you have a very good written field procedures. And then when you're conducting your inspection, for the coating anomalies, for instance, where you have 3 different techniques, from current attenuation, ACVG and DCVG, if you're working towards that indication, you're making sure it is properly validated in the field. So once it's properly validated, you collect all your data sets. Then after that, you want to make sure that it's properly aligned. So can I share my screen or something I can talk over? Okay,
you can try, sure.
Okay.
I think you have permission to do that.
Okay, thanks. Share my screen. Okay, so if you go to this slide, you can see at this specific location, the technicians have gone to the field, they collected all the data sets, they do all their validations, and then you are trying to align at which specific location do I have a coating anomaly for this instance. You can see the blue line, that is a drop in the current level. The red line shows you very high attenuation rate. You look at your ACVG and DCVG, you have indications here. So using an advanced, will I say software, an advanced indirect inspection tool is going to give you that opportunity to be able to properly align your indication to have a high likelihood of success. And if you go to the next slide, on the left-hand side, this is where the anomaly is. On the right-hand side, this is when the pipe was exposed. So even before the pipe was exposed, and to tell you, I was actually the lead engineer that worked on this project, I already knew what I was going to expect because the inspection was done properly in the field. We had the field procedures were developed, the anomalies were validated in the field, the indications were aligned, classified, and prioritized based on the severity. The pipe was exposed, and it actually confirmed the exact prediction.
Awesome. Okay, no, that makes sense. No, thanks for that. So jump to the next question here. So, it is important to select the appropriate flow and corrosion models when you're doing an ICDA program. And so NACE has a technical report, 21410, that provides kind of step-by-step predictions or procedure of how to select your models. And this, technical report is referenced in all 4 ICDA documents every time it comes out. Do you have any comments on the use of this technical report and the selection of flow and corrosion models?
Yeah, I saw that question from Dr. Shankar. I think I will follow up with him offline because there's a lot of information required, but just coming from real life, practical experience, all the whole models, like there's Dr. Shankara model, there's Stevens, there's Palacios. These are very reliable models that, based on industry best practice, they really work. So if you go to Appendix A of this SP0116 for multi-phase pipelines, all those conditions are detailed there. So there's all the specific model give you what are the conditions. And then if you go to crude oil pipeline, Appendix A to C, the specific guidelines and condition of the flow and what has to be done is documented there. But personally, I'll follow up with Dr. Shankara to be able to understand what he's asking. But overall, Stevens, Palacios, Shankara, those are proven models that actually work that I've personally used.
Perfect. I think that probably at least gives the audience a good feeling and understanding. So thanks, Shankara, for that. So another question here. So, excluding when you're using an ILI to help with this, what do you feel is the most effective method for helping detect when you have external corrosion occurring under desponded but intact tape coating? Because that is always a big challenge for the industry.
Yes, Brett, I think I've received these questions more than 20 times in every NACE conference. And I'm just going to address this based on industry best practice. When the pipe is a buried, coated, and cathodically pipeline, has a very high dielectric shielding coating, and the pipeline is new, probably rule of thumb less than 20 years, even overall, inline inspection is the best tool for assessing that pipeline segment. The reasons because it's high dielectric, it shields, water gets into there, the CP cannot get to the pipe, you're having external corrosion, you can even do overline survey, it shows the pipe is protected, but you're having a very big problem. Inline inspection is the best tool for that specific instance. But however, If the pipeline is not piggable, that you cannot run like inline inspection tool, the success rate of using the advanced indirect inspection tool relies on the age of that pipeline. So when I mean by the age, that tape coating would have been in the soil for a very long time. There would have been soil stress, there would have been operational issues. So the coating quality might have degraded to a certain level that CP can get to the pipe. So the older the buried pipeline, the higher the likelihood of indirect inspection techniques on pipeline coated with shielding disbonded coatings. But in overall, inline inspection is the best assessment technique for that pipeline.
Awesome. Can you, so unfortunately with that, we have a hard stop. We need to stop right now. Unfortunately, we can't answer some of the other great questions in here. So thanks everybody for your participation. If you would like, to get some answers from Chuks, he sent his contact information on there. This will be posted on YouTube, on our YouTube channel, so you can be able to review it and be able to send him emails, and that's great. So thanks again for that presentation and wonderful QA session. So upcoming in our webinar series, we have Mark Wynokowicz from Synovus in about 3 weeks' time. So please follow our LinkedIn page and website when that registration goes live. And if you're interested in sharing your research experience or any other interesting case studies with the industry on this platform, please email me at program@nacecalgary.ca and we'll work to make that happen. Thank you everybody for joining us today. Please be safe out there and have a good rest of your week. Goodbye.